Okay, it's time to continue with relativity. So last class period, I introduced the principles of relativity, which were, or postulates. The laws of physics are the same in all inertial reference frame. So it's very important that we understand what an inertial reference frame is. So, Nate, what's an inertial reference frame? Yeah.
The initial reference frame is
Perfect. Inertial reference frame is a reference frame that's not accelerating. And so everything we're doing in special relativity is working in inertial reference frames that are not accelerating. So that's called the principle of relativity. The second one, the constancy of light. The speed of light in vacuum is the same in all inertial reference frames, and it's in vacuum, I should have said that, regardless of the motion of the source or observer. So it doesn't matter how you're moving, as long as you're moving at a constant velocity, inertial reference frame, you're going to measure the speed of light to be exactly the same. So with those two postulates, we come to some preposterous results. So, well, let's just go straight to the example. When we talk about things occurring, we talk about events and we usually say, okay, so let's meet at my house at 1 p.m. to watch the Man City dominate whoever they happen to be dominating that week. We have to have a location and a time. And so when we talk about events, we don't specify just the location, just the XYZ coordinates, but we specify 4 variables, X, Y, Z, and the time. So we need all 4 of those things to talk about an event. And we're going to look at how events are perceived in one reference frame compared to another. So here we have 2 people. We have A is for Abe and B is for B. Very tricky in the naming convention here. And so we have the same situation as viewed by 2 different inertial reference frames. So we have Abe. Abe is in his spaceship, and Abe sees B flying toward him. And then Abe sees, you have to go to the bottom slide, Abe sees 2 stars that went supernova at the same time. Now, how does he say at the same time? Well, the light got to him at the same time from both. And so, taking the distances away, you can see the picture, trying to make them so they're equal distance away. He calculates, okay, so I got them here. This one's this far away, so it took this amount of time to get to me. This one's this far away, it took this amount of time to get to me. And he determines the 2 stars explode at the same time. When the 2 stars exploded, B wasn't next to him. B was approaching. But the light got to him at the same time B got there. So that's Abe's observation. He says, the 2 stars exploded at the same time because I had these 2 stars that were same distance away, stationary with respect to me. The light got to me at the same time. But if we look at B's reference frame, B doesn't see herself as moving. How does she see herself in her reference frame? Stationary. That's what it means to be in your own reference frame. You see yourself as stationary. And so she sees herself stationary, and A is coming toward her. Now, because the light arrived at both of them the same, you go down to the bottom one, and you have the light arrive at both of them the same. But she sees that the stars that produce the light themselves were moving. And so in her perception, if she extrapolates back, because of the motion, she actually perceives that the one that was in front of her was the one that gave off its light first. And the one that's behind her gave its light off second. So they didn't explode at the same time. Now that's preposterous, right? You have 2 different people doing good, perfect physics, no mistakes. Abe says the 2 stars went supernova, I say exploded, collapsed and then erupted, at the same time. And B says, no, it was first the star in front went supernova, and then a little while later, the star behind went supernova. Who's right? That's the key to relativity right there. They're both right. So we have to find a way to warp the space-time continuum so that they can both be right. That's what Einstein worked on figuring out first. That's what he wrote in his paper in 1905, was how to deal with a problem like this. Yes. The key here was in B's frame, the flashes don't travel to equal distances. A thing to notice is in B's frame, the distance from where she is to the front flash is much larger than the distance from where she is to the rear flash. Whereas in A's frame, the distance is the same. So what do we do? Here is an example of just regular physics. This is not relativity calculation yet. It's regular physics, classical physics. You have a high-speed jet of charged particles coming from the core of NGC 6251. NGC is New Something Catalog. I can't remember what the G stands for. But it's a catalog of different things in the sky. And so you have a jet of charged particles coming toward you. And so those charged particles are giving off radiation. You measure that radiation, and the charged particles are coming toward you fast enough that if you take the distance traveled, if you take the light arriving, you calculate the speed of the jet, you calculate that the jet is moving faster than the speed of light. But that's not possible, right? And so the key is, because the jet moves forward, the actual time that it takes to get you is less. 1 day later, it's going to take less time by a day, surprisingly enough, than it did a day earlier. And so when you take that into account, you find that, the jet's moving really fast, but not fast as the speed of light. Now, I know that I thought about taking these out because I don't think that they're all that useful, except for how do we calculate the time that it takes? Well, the time is the distance over the speed. And so if you had the jet move forward some distance delta x, then the new distance d prime is going to be the original distance d minus that delta x. Delta x is the speed of the jet multiplied by 1 day. And that's how you end up resolving it. Let's get to, this is the key slide for the entire lecture, Einstein's clock. So Einstein proposed, let us imagine that we have a light-based clock. We have a clock that consists of a light bulb, a mirror, and a light detector. And so the light bulb flashes, light goes straight across this clock, hits a mirror, reflects back, and hits the detector. So the light's just going to go boink, boink, hits the detector, and you say that's 1 tick of the clock. So if you're inside, if that clock is stationary with respect to you, so you're inside the room with the clock, how long is the tick for that clock? How can I calculate the time for the tick of the clock? Okay, the distance it travels is 2d, and then I divide that by speed of light. So I have the time for a tick of the clock, and I'm putting a 0 here because it's the rest one, is equal to 2 times the distance divided by the speed of light. That's pretty simple. Now we're going to have, the clock is in a railroad car. You can see above and below that room, you have the little, it's supposed to be wheels on a track. So the clock's in a railroad car, and the railroad car is going past you at some very fast speed. Once again, this is a Gedanken problem. You can't make a railroad car that goes like 0.8 times the speed of light. But we can do the calculations to say, what if? So let's say we have it moving with speed v, and v is very large. So v is greater than 0.1 times the speed of light. How do I find the time for a tick here? What's the first thing you note just looking at the picture? Say louder, Aaron. It's a longer distance the light has to travel. Since the light has the same speed in all reference frames, then that longer distance means it takes more time to tick. So how do we go about calculating that time to tick? Well, first we're going to need to determine what the distance is, because our basic equation was the distance divided by the speed. So if I take this and break it into pieces, I have a distance that I just marked in black that would be 1/2 the time for a complete tick multiplied by the speed at which the railroad car is moving, at which the clock's moving. Why 1/2 the time for a tick? Because that takes half of the time to go hit the mirror, the other half time to come back. So if one side of a triangle is 1/2 delta t v and the other side is d, how do I find the hypotenuse? I use the Pythagorean theorem. So the distance of this, I will put d prime is equal to the square root of d squared plus, oh, the colors aren't working out. D prime is equal to the square root of that, right? Just the Pythagorean theorem. So if I want to find my delta t, the time for a tick in this case, I am simply going to take 2d prime over the speed of light, substituting that d prime, that's 2 square root d squared plus 1/2 delta t v quantity squared all over c. Well, shoot. What do you notice about this equation that makes it a little bit of a nuisance to solve for delta t? There's delta t in there twice. So what I'm going to do is I'm going to square both sides. So delta t quantity squared. Actually, let's multiply the c across. You want to? Okay, thanks. Delta t squared c squared is equal to 2 squared is 4. D squared plus 1/2 squared is 1/4. Delta t squared v squared. Now I can bring the delta t's together and solve for delta t. Did I make a mistake?
Why do you square the stuff inside the square root? Don't you just...
Because there's a square sign right there.
Oh, I got it.
Everybody clear? I don't want to mislead or leave somebody like, he lost me. So I'm just going to take this term and bring it over here. Notice 4 times 1/4, conveniently enough, is 1. So I'm going to have delta t squared times c squared minus v squared equals 4d squared. I'm going to do another thing that seems kind of silly. I'm going to factor a c squared out of that c squared minus v squared. I'm doing it because it makes my final answer look prettier. Well, what was I trying to solve for? Delta t. So I have to divide everything by this and then square root. So delta t is equal to the square root of 4d squared over c squared times 1 minus v over c quantity squared. Everybody still with me? Now, I did not put a plus or minus sign. Why not? Yeah, it's not going to be a negative time for the tick of the clock, right? We have to think about these things. We can't just throw out the idea that when you take a square root, you have two results. But then we use our reasoning to say, but I can immediately discard one of those results because it's non-physical. Simplifying this, that's 2d over c times 1 over the square root of 1 minus v over c quantity squared. Huh. What is that equal to? So now I can relate the time for the tick if the clock is stationary compared to me being stationary, seeing the clock travel by at speed v. And I have for my final equation, and I'm going to come up to the top now to put, well, I'll put it down here first, just for completeness. So when you come look, if you come look at these at a later time, so that's the equation to relate the time in one reference frame to the time in another reference frame. So we have our final equation, delta t is equal to delta t0 times 1 over the square root of 1 minus v over c quantity squared. Now, to save ourselves some time, we have some abbreviations. We define beta is equal to v over c. That just makes it easier to talk about the speed. It's giving us the speed in units of the speed of light. So if beta is 0.8, that means the speed of light is 0.8 c. And that means that I can write this thing in parentheses, or in the square root, as 1 minus beta squared. Easier to write. Second is we define gamma, I should put 3 because it's defined, as 1 over the square root of 1 minus beta squared. So using that abbreviation, this is delta t aught times gamma. Now, before I go to the next slide is going to talk more about this equation. But let's point out beta, the speed. What's the minimum speed that a particle can have? Not velocity, but speed. 0. So if beta is 0, what is gamma going to equal? 1 over the square root of 1 minus 0 is 1. Okay? Now, as the speed increases, what's the maximum value beta could ever reach? Well, speed reaches a maximum value of c. So what's the maximum value for beta? 1. So you can have something approach beta equals 1. If beta equaled 1, you would have divided by square root of 1 minus 1, which would be 1 over the square root of 0 is infinity. So gamma approaches infinity as the speed approaches the speed of light. Gamma is never equal to infinity, but then again, the speed is never equal to the speed of light. Important things, gamma is always a value that's greater than or equal to 1. It has no maximum limit, has a minimum value of 1. The faster you go, the higher gamma. The larger gamma, the bigger the difference in the time between the ticks of the clock. So we have to define a few more things. We'll define the rest frame. Rest frame means the frame in which something is at rest, not moving. So the clock's rest frame is the reference frame where the clock is not moving. So if you're in an airplane and you look at your watch, is your watch in its rest frame? Once again, it's really important to be able to get these ideas down or you can't do the problems. By definition, in its, the watch in its own frame is going to be its rest frame. And if it's on your wrist frame is the same as the rest frame of the watch. In the rest frame, you measure the time delta t0, which we call the proper time. Proper does not mean correct. Proper is the proper one to use for comparison in the equation. And because our equation had delta t is equal to gamma delta t 0, and gamma is always greater than or equal to 1, then that means the proper time is always going to be less than the time in any other reference frame. So now we can put this into a perspective. If I am on the airplane and I look at my clock and I say, my clock ticks once every second. So the delta t 0 is 1 second, the time per tick. If I'm flying in my airplane at 0.8 C, right, ridiculous, but if I'm going at 0.8 C and you're on Earth, what are you going to observe for my clock? What's the delta t that you observe going to be? Is it going to be 1 second, bigger than or smaller than 1 second? It's going to be bigger. So you're going to say Richard's clock, it registers 1 second in 2 seconds, which means that Richard's clock is running really slow. And so he's going to think that less time has elapsed when he lands. The only thing is, we're both correct. So it's not going to be, I think less time elapsed, less time will have elapsed. So when I land, I will have aged less than the person who was sitting on Earth watching the flight. So we might have started the same age, but we end up with me being younger because I was flying. Now this brings me to a great book series. How many people have read the Ender's Game book series? Got a couple. In Ender's Game, it's written by a guy with a physics degree. And one of the key principles is relativity. That you had people who, I know I'm giving away some of the plot story here, but you had people that flew away from Earth right after the first bugger war ended, and they've been flying at near light speed for, 40 years? Something like that. But if they're traveling at near light speed, the rate at which time is passing for them is different than the rate of people on Earth. So they've only aged like a couple years. And if you go to the later books, Ender Wiggins travels around the universe traveling at close to the speed of light for long stretches of time, so that he's writing books about his life 1,000 years after, the events occurred. And it's really funny. Well, not funny, ironic. In trying to humanize the buggers, everybody demonizes him that he is, under the genocide. Anyway, it's a great book series to read, especially if you're interested in relativity, or if you got some interest in quantum mechanics and things like their Ansible runs by having two quantum entangled particles that allows faster than light communication according to theory. So just it's a great book to read. Pick it up on Sunday. Yeah. Be done by Tuesday. If you don't go to class on Monday, or if you read faster than I do. Okay, so coming back to this, the proper time. Proper time means the time measured in the rest frame of the clock. And it's always going to be the shortest time possible between two events. A reference frame different is going to measure a longer time. And the way to relate those values is this equation, where gamma is based on the speed of one reference frame with respect to the other. Notice the red here, really important. The clock remains stationary with respect to events if you're going to measure the proper time. So if I'm measuring the time for my heart to beat, if the clock is stationary with respect to my heart, it'll measure the proper time for my heartbeat. If the clock is moving with respect to my heart, it's going to measure a dilated time, a longer time. So time dilation, times are longer in any other reference frame. The proper frame is always the shortest possible time that can be measured. Okay, how to solve problems. Oh, you got a question, Mahala?
What would be the condition where the clock is moving? Because we talked about if you're on an airplane and it's not moving.
Yeah, so if the example of me being on an airplane, Relative to me, the clock is stationary. Relative to a person on Earth, the clock is moving. So if I were to measure what's going on for a person on Earth, my clock is moving with respect to them. Agree? And so I'm going to measure a dilated time for something that occurs for the person on Earth, which leads us to a paradox that we will have in just a few slides. Okay, when solving time dilation problems, as you will be doing over the weekend, identify the two events that mark the beginning and ending of your timing. The clock is whatever you're measuring it with. Make sure you identify which reference frame is the rest frame, the one that's going to measure the proper time between those two events. So if it's the rest frame, the clock is stationary with respect to the two events. And then make sure you calculate this gamma. I always start off by calculating the gamma because I'm almost certainly going to use it if I'm doing relativity. So calculate that gamma and then put it into your equation. So we usually write speeds as fractions of the speed of light. It's important that you know what a light year is. I used to just gloss over this, but then you find people who were confused. Because when you say a light year, a lot of people think that means it's a time because a year is a time. Light year means the distance that light travels in 1 year. So the definition of 1 light year is equal to the speed of light multiplied by 1 year. That's the definition of a light year. And so we can do things like, well, what is that distance? Distance is equal to I actually have to think this. Speed is distance over time. So distance is equal to speed multiplied by time. So I can take this, and if it's a light year, that's going to be the speed of light, c, multiplied by the time, and you just multiply those through. It's the same equations I had above. 2,997,92458 meters per second times the number of seconds in a year, which I'm just going to put as 1 year because I don't know that number. Let's move to our first clicker question. A sprinter runs a 100-meter race at a constant velocity, which means same direction, same speed. Who measures the proper time for this race? Is it going to be the sprinter, the official timekeeper, neither, or both? Right now, we have one for everything. Actually, everybody's answered. No, Paris, you haven't. All right. We had 6, 10, 0, and 2. This is the perfect time for you to discuss with your nearest neighbors about your reasoning, how you determine which one is measuring the proper time. Okay, let's go ahead and re-answer. See if your neighbors helped you or hindered you. All righty. After discussion, we had the two people said both moved to only one could be correct, and they went with B. And one person changed from the sprinter. Okay. Larissa, your question is actually not going to be answering the full question. It's going to be a partial. How do you determine where you're going to measure the proper time?
I don't even understand that question.
Okay, somebody want to help her? How did we? It's what?
When you started, when you ended, I don't understand how to answer that.
Okay, somebody want to help her out? Okay, James.
So to decide where you're going to have your clock stationary, I guess, so where the clock will be placed, you have to see what the distance is being measured relative to. So if the sprinter is running on Earth, the distance is relative to a point on Earth, so the clock has to be stationary with respect to Earth.
Is that what you're going to say? Or are you going to say something different?
Say the rest frame.
Okay, she was going to say the rest frame. It's actually Brandy that has the right answer here. It's the rest frame that's going to measure the proper time. So the rest frame is the reference frame where the start and end are the same place, right? Where it's a rest with those. So the runner and the starting line are the start. The runner and the end point are the end. What reference frame has those as the same location? The sprinter's reference frame has those at the same location. And so it's actually going to be the sprinter who measures the proper time. Now, we can go through and do the calculation. Which calculation are we ready to do here? It says it's a 100-meter race at a constant velocity. That 100 meters we assume is measured on Earth. If it's measured on Earth, then we can take the velocity and the 100 meters and calculate the time, but that's going to be the time measured by the official timekeeper. Right, so the official timekeeper says delta T is equal to the distance over the speed, which let's just make up a ridiculous speed. Let's say that the runner is traveling at, well, no, let's be realistic. Let's be realistic, because my next clicker question goes to the ridiculous numbers. So the distance is 100 meters. How fast do you suppose the sprinter's running? Miles an hour, really? Let's go with a reasonable 10 meters per second if you're world class. Not reasonable for you and me. Okay, 3 to significance. Delta T is 10.0 seconds. That's the time measured by the person on Earth. What does the runner's clock measure? Delta T 0, since we had the equation delta T is equal to gamma, delta T 0, then delta T 0 is going to be delta T divided by gamma, divided by gamma. And so that's going to be, got to calculate that gamma. Remember I said I do that first. 1 over the square root of 1 minus 10 meters per second over 299792458 meters per second. Okay, come on, erase. What do I get when I divide 10 by 3 times 10 to the 8th? A really small number, and if I square it, much smaller. So this number is approximately equal to 1. Now, we actually have a binomial expansion that says, in truth, it's equal to 1 plus 1/2 of 10 over 2.997 times 10 to the 8th. Okay, so that's a really small difference between 1 and gamma. But the time that the sprinter determines that his clock said is actually going to be a little bit shorter than what the person on Earth said. But at the same time, the distance that he thinks he ran is going to be shorter than the distance that the person on Earth says he ran. So he can feel, okay, I kind of, or like contraction. Yeah, it works out that he feels okay. Next question. An astronaut leaves Earth in a spacecraft moving at 0.8 C and travels to a star 30.0 light years away as measured on Earth and back. Who measures the proper time for this trip? Oh, sorry. You can answer now. My mistake. Okay, we had 13, 4, 1, and 0. This is almost exactly the same as the last one, right? Except for you have one crazy difference. Where's the starting point? Earth and the rocket. Where's the ending point? And the rocket. And so you're like, the starting point and ending points are the same location in both. But in which reference frame, is the clock stationary? Let's go through and analyze this more before we come back to it. So, a 20-year-old astronaut named Ashton, okay, I changed the name to match my grandson, leaves the Earth in a spacecraft that's traveling at 0.80 C. How old is Ashton when he returns from a trip to a star 30 light years from Earth, assuming that he moves at 0.8 C relative to Earth the entire trip? How would we solve a problem like this? Okay, we need to know how fast it is, and we have that. So we have right here, beta is equal to 0.80, right? Speed is 0.80 C, so beta is 0.80. Once I have that, I immediately say, well, let's calculate gamma. And this is chosen to be easy. 0.8 squared is 0.64. 1 minus 0.64 is 0.36. Square root of 0.36 is 0.6. And so it's 1 over 0.6. So what does that give us? So there's my gamma. I just calculate that off the bat because I know I'm going to use it. Now we have the distance is 30 light years as measured by Earth. It says, did I not write here? Well, it doesn't say as measured by Earth, but I meant it to say that's measured by somebody on Earth. So if the distance is measured on Earth, we can calculate the time measured on Earth is equal to the distance divided by the speed. So the time, and I'm going to break this into halves. The time to go from Earth out to that object is the first half, right? So I'm going to call this 1/2 of time on Earth is the time it takes to go out the distance d. So my distance is 30.0 light years. My speed is 0.80 c. Remember that that's 30.0 c times a year, using the definition of a light year. divided by 0.80 C. The C's cancel. 30 divided by 0.8 is equal to what? 37.5. So the time that's measured by somebody on Earth is 37.5 years for the entire trip, or for the half of the trip. Now for that half of the trip, so we're only focusing on that half of the trip. On that half of the trip, both people are in an inertial reference frame because the astronaut's traveling at constant velocity. The person on Earth is at a constant velocity that we consider rest. Who's going to measure the proper time for the half trip, for going from Earth to that star? The astronaut. That's the question that's exactly like what we had before. And so we're going to have 1/2 delta time Earth is equal to gamma times 1/2 delta time for the astronaut, by using our time dilation equation and recognizing that 1/2 delta time astronaut is proper time for half the trip. Because that was exactly what we had in the previous problem. So that means the time that's measured by the astronaut, we can now, if we have half the time, we can double it. I'll get rid of the 1/2s now. Delta time for the astronaut is equal to delta time on Earth over gamma is equal to, and the delta time on Earth is going to be 2 times 37.5, which is 75. 75.0 years divided by 1.6 repeating. And what is that? 0.6 times 75.
44.9 repeatings.
So the time for the trip as measured by the astronaut is 45 years. And the time for the person on Earth for the entire trip, 75 years. Now, if we just look at these numbers and if we say one's the proper time, which one would it have to be? Has to be the astronaut because the proper time is always the shortest possible time. Now, where is the problem here? Have you guys heard of the twin paradox? Okay, the twin paradox is what we just did in a nutshell. The twin paradox says we have two twins, so Ashton and Betty, and one of them is put in a spacecraft and travels out and back, and the other one stays on Earth. And as they're traveling out, the person in the spacecraft, Ashton, says, I'm stationary and I see Betty moving really fast. If Betty's moving really fast with respect to Ashton, what does Ashton record for the time of the clock ticking in Betty's reference frame? Slow. So Ashton says, Betty's not aging as rapidly as I am. But Betty, being on Earth looking at Ashton, what does she say about Ashton's clock? She says his is slow. And so Betty says Ashton's the one that's not aging as fast. Well, when they come back together, they can't both be right on that, can they? They can't each one say, by golly, you're a lot younger than me. One of them's going to have to say, I'm the younger one, or they could both be the same age. So that's why we call it a paradox, because we have two conflicting predictions. And I've said all along that this relativity thing, they're both correct. And so how can, of course, I'm the teacher, I play it up, and I ignore one flaw in the whole process. If you already knew the answer before I started, don't blurt it out. But if you figured it out just by listening, what's the one flaw in this paradox? What is the basis of all of the special relativity we've learned? Being in an inertial reference frame. Well, who's an inertial reference frame for this trip? The person on Earth. Because the person in the spacecraft, even assuming magic, they had to accelerate to start the trip. They had to accelerate to stop and come back. And they had to accelerate to stop the trip. So they had these periods, the acceleration periods, that we can't apply our special relativity rules to. Now, the person on Earth was stationary the whole time. They can do their special relativity calculations throughout the entire trip. But the person in the spacecraft can't. So that means the person on Earth is the one that has the correct answer. So the person on Earth says what we calculated here, that the person on Earth is age 75 years. So if you start at 20 years, they're now 95 years old. The person on spacecraft, only age 45 years, they're now 65. Significant difference. And so where's the variation? The person in the spacecraft will have observed that the person on Earth aged a lot just when the spacecraft left. And then they aged really slowly during the trip, and then aged a huge amount when the spacecraft turned around, and then aged a small amount during the trip, and then aged a lot when they stopped. So that we have agreement between, and that's general relativity that you have to use to do those calculations where they age really rapidly during the acceleration periods. So it's not a true paradox. I mean, it can't be a true paradox, or else we've got something broken, because the person in the spacecraft is not the entire time an inertial reference frame. Cool though, isn't it? Now to length contraction. We learned about time dilation. The time it takes to go from point A to point B is different in the two reference frames. But each reference frame agrees on speed. If Gabriel's running toward me, I'd say, Gabriel's coming toward me at 5 meters per second. But if Gabriel says I'm stationary, he'd say Richard's coming toward me at 5 meters per second. We agree on the magnitude of velocity, it's just the direction that we disagree on. And so given that distance is equal to speed multiplied by time, if we agree on the speed but we don't agree on the time, what does that mean about the distance? We're not going to agree on the distance either. And in fact, I'm going to forego, this is once again using Abe and B, and Abe and B are one's traveling next to the other, and we suggest a way of measuring the length. Length is the speed multiplied by the time that's elapsed. And of course, for Abe and for B, you have different times that elapsed. And so if you put those together, this is really just using this equation. Distance is speed multiplied by time. So distance on Earth is equal to speed multiplied by delta time on Earth. Distance in the spacecraft is equal to speed multiplied by delta time. I should have used A for, instead of Earth, I'll use B just to be consistent with the picture. A. And so if we just take these and we relate the two, just divide the two, so the V's cancel out. Then you have the ratio, well, dB is equal to dA times delta T B over delta TA. And when you put that together, that's what this equation is showing. And you find that the length measured by Abe is equal to the length measured by B divided by gamma. So the length also shifts. Which length is longer? Which one's shorter? We use a different proper frame for distance than we use for time. So we worked on determining which is the proper reference frame for a time. It was the reference frame in which the clock was stationary. I went quickly past the slide that said, in short, a moving clock runs slow. A stationary clock is the one that keeps the proper time, which is the longest possible. So now we get to this for the proper distance, the proper length. We measure the proper length in the reference frame where the object is at rest. So if it's a meter stick, in the reference frame where the meter stick is not moving, you measure the proper length. And in any other reference frame, it's shortened. So the proper length divided by gamma gives you the shortened length. So if we go back to the problem I did, we had a distance that was 20 light years. That was measured by somebody on Earth. Is that going to be the proper length for the distance between Earth and the star, or a contracted length? The question you have to ask is, was imagine that there's an object that goes from Earth to that star. Was that object stationary as measured by Earth, or was it moving as measured by Earth? Stationary. If it's stationary as measured by Earth, then the Earth is the proper reference frame for measuring the length. So this is equal to the proper length. So the length that was B. So the length that Ashton saw was the contracted length, which is the proper length over gamma. So that would be 20.0 light years divided by 1.66, repeating. And if you divide that, we're out of time now, but you're going to get something like 13 light years is the distance that the person in the spacecraft saw for the trip. They didn't see it as long of a trip because both the time and the space were warped, hence the warping of the space-time continuum. Here's my problem-solving strategies. Make sure you identify the object whose length is to be measured, and the length contraction only applies in the direction of motion. So if I am moving like this, the length stays the same, the height stays the same. It's only this dimension that changes. Hence, if you want to look good, if you're fat like me, you travel so that your belly is going forward because that'll make it look like you're thinner that direction. If I went the other way and traveled head first, I would look shorter but keep my width, and that would be bad. Okay, have a great Sabbath.